In the last video, we looked at how the conservation rules can be used to tell you which interactions are possible and which interactions are not. In this video, we're going to look at how it is you can create quarks and antiquarks. Now, there is a process called pair production, where matter and antimatter can be made in equal measure. Quarks can be created as long as there's equal number of quarks and antiquarks of the same type. Now, there are interactions that can create quarks and antiquarks of different types, for example, the weak interaction. But we're going to focus now on creating quarks and antiquarks of the same type. So an up quark and an anti-up quark, or a down quark and an anti-down quark, and so on. So you can see here there's two ways of creating strange quarks. Either decaying from a more massive quark, which isn't part of your specification, or by creating equal numbers of strange quarks and strange antiquarks. And this is where it gets exciting, because that's where the story ends for A-level physics. The strong nuclear force can create quarks and antiquarks in equal measure. Brilliant. But we can go further. We can go much further. So let's start here. Fundamental charges. It's a bit of a weird concept, but mass has one flavor. All mass is attractive. There's only positive mass. We've never detected any evidence of negative mass. Whereas electric charge has two flavors, positive and negative. And the interaction is interesting. Like charges repel, unlike charges attract, and we can use Coulomb's law. But if you remember, right back at the beginning of this series, I said the graph for the strong nuclear force was much more complicated. And it is. The strong nuclear force acts between particles that have a different sort of charge, which 𝗟𝗟𝗀 called color charge. And he only called it color charge because we needed another way of identifying with this type of charge. And unlike gravity, which has one flavor, an electric charge that has two flavors, this type of charge has three flavors. And three anti-flavors. Red, blue, and green is how we name them by convention. But don't confuse this into thinking the particles actually have those different colors. They're just a way of labeling this color charge that the particles can have. And so particles can have a selection of these different charges. You can have particles with no charge, but they have got mass. Or you can have particles with mass and with charge. You can have particles with color charge and electric charge and mass. So you can get a selection of all of these. Now, there are four fundamental forces in nature that relate these three fundamental charges. Mass experiences the gravitational force. Charge experiences the electromagnetic force. And it's color charge that experiences this strong nuclear force. So only quarks have color charge. Leptons don't have color charge. And then, of course, there's the fourth force, fundamental force there, turning mass into energy and vice versa, rather than producing a measurable acceleration on particles or something like that, which we might naturally think of as a force. So why did 𝗟𝗟𝗀 pick color as a model for this new type of charge? Well, it's because of the fact that you get three quarks combining to form a baryon. The idea is that particles have to be color neutral. That means that a quark has to contain a red, a blue, and a green color quark in order to have the overall color of the baryon as white. So it's color neutral. Antiquarks carry the anti-colors. So anti-green, sometimes called magenta, anti-red, sometimes called cyan, and anti-blue, sometimes called yellow. And so anti-quarks carrying those three colors can combine to form an anti-baryon, because anti-red, anti-blue, anti-green, or cyan, magenta, and yellow, when mixed together, form white, so color neutral. Now, this model's built up on the observation that there are always three quarks or three antiquarks in a baryon or antibaryon. That's what makes this model come together. What's fascinating is that quarks don't have a fixed color charge. They change their color charge. And that's what gluons do. When a gluon is exchanged from one quark to another, it carries with it the color charge and swaps them round. It's constantly changing the color charge of these quarks. This subject is called quantum chromodynamics. Quantum because the colours can only have certain values. Chromo referring to colour. And dynamics, the idea that these are changing. But again, the world's not quite done with being fascinating yet. Gluons don't just carry one colour charge. They carry two. They carry a colour charge and an anti-colour charge. Gluons have two different colour charges. A colour charge and an anti-colour charge. Quarks have either a colour charge or, if they're anti-quarks, an anti-colour charge. Gluons have both. And you can mix and match. So that's why it seems a bit odd that there are 8 types of gluon. So on the face of it, it looks like there should be 9 types of gluon. You could have a red anti-red gluon, a red anti-blue gluon, a red anti-green gluon, and then you could have a blue anti-red gluon, a blue anti-blue gluon, a blue anti-green gluon, and so on. This symbol in the middle means OR in statistics. So you could have this type of gluon, or this type of gluon, or this type. And in probability, when you multiply probabilities together, you are saying AND. So this string here is the probability of this and this, or this and this, or this and this, or this and this. And one of the ways you can write that is using a plus and then using some normalizing factor to make the probability back to 1. You've done probability probably further down in your schooling, where you may have learnt that when you say the probability of one thing and another, you multiply the probabilities. But the probability of one thing or the other, you add them together. And so if I have a gluon, it has a probability sat with this equation, where these are pluses, these circles with pluses in them, then multiplied by some factor that makes the overall probability 1. That looks quite nice, but it's not quite right, because that's 9 combinations, and I've just said there are 8 combinations. Well, let's see if we can knock some of these out with some basic classical thinking. A red anti-red gluon is colourless, as is blue anti-blue, as is green anti-green. So those are colour neutral, which means they wouldn't interact with quarks. So if they do exist, then their range would be infinite. They wouldn't interact with anything. We wouldn't be able to detect them. So if we can never detect it, and it doesn't interact with anything, why say it exists at all? We're going to employ Occam's razor. Occam's razor is the idea that if we've got a model that works, and there's another model that works that's simpler, use the simpler model. There's no point having a more elaborate model if it predicts the same results. There's also an idea here that red anti-blue gluons would interact with red quarks and blue quarks. Well, so would blue anti-red gluons. So they would be indistinguishable from each other. So we can start bunching together some of these gluons and saying, well, if they're indistinguishable, let's just say they're one type of gluon. And we can do the same thing with red anti-green, green anti-red, and with blue anti-green, green anti-blue. When you do that, you end up with 3 gluons. Oh, hang on, I said there were 8. I've gone too far the other way now. Again, this is a probability expression. So this is red and anti-blue, or blue and anti-red, and then multiplied by some factor to normalize that probability back to 1. So where are the others? Well, I'm going to show this list, and I'm not going to explain it because I don't understand it. See, it turns out our classical physics way of looking at things, little particles bouncing around and interacting with each other, is severely limited. That's not the way the universe really is. These particles, and all the other particles that you've seen in the particle zoo, those symbols are wave functions. They are functions that tell you the probability of a particle, the probability of its energy, the probability of its momentum, the probability of the particle. How likely is it to be where you think it is, and to be what you think it is? That's all tied into those wave functions. And wave functions can interact with other wave functions through various matrices or any other sort of operator. And that's what you're looking at here, is 8 unique operators that will be used to transform one set of wave functions to another set. Incredibly complicated and sophisticated mathematics. When you look at these, you think, what does the I represent? That's the square root of a negative number, square root of -1. So you've got imaginary things here. And if you look at the last one on this list, red anti-red, blue anti-blue, -2, green anti-green, Well, is there a blue anti-blue, red anti-red, -2 anti-green, 2 green anti-green? Well, yes, but it does the same thing. So there's all sorts of other ways of writing these gluons, but you don't need to. So we're going to use Occam's razor. The minimum number we need for all of our strong interactions is these 8. But there are other formulations of this. We just don't need them. Now, I know this is complicated. It is complicated. That's why particle physics is famously a difficult subject. And we desperately want to try to visualize it in terms of lumps of matter moving around. The classical physics analogies that we try to use, just they don't work for particle physics, which is a real shame because it'd be lovely if they did. So instead, we have to use complicated things like this. These are wave functions that you use to transform one wave function into another wave function. Okay. If we did want to have some sort of visual representation of these quarks and gluons, then for A level, this is what it looks like. Notice I haven't included the charm quark, the top quark, or the bottom quark here. But I have included the 3 different colours of up, the 3 different colours of down, the 3 different colours of strange, the 3 different colours of anti-up, anti-down, anti-strange, and all 8 gluons, whatever they are. It looks like quite a lot. Again, we have this really lovely picture with quarks, and we managed to get that list of fundamental elements that the universe was made out of into a smaller number, and now we've just increased it again. And we have increased it again, but it's not too much. You can find diagrams like this that are supposed to help you see which gluons are exchanged between which quarks. So a red quark here and a green quark here, there are certain gluons that can be exchanged between them. This gluon here, G3, whatever that is. But this quark here and this quark here, they can be, the interaction between those 2 quarks can be this gluon or this gluon. Now you'll find particle physicists love diagrams like this because it helps them understand what's going on. But if you don't really know what the gluons mean, then they're not actually much help. So let's try for a nice, easy classical physics model of what's going on. If you look here, you can see that within each of these baryons, this is a proton, this baryon, there are gluons being exchanged. The gluons carry a charge and an anti-charge. When those gluons are exchanged, they switch around the color charge of those quarks. But overall, the quark remains white. It still has red, blue, and green inside it. Now, those gluons cannot go very far. They can't go very far because they exchange gluons with other gluons. But the gluons can decay into quarks and antiquarks in equal number. Now, those quarks and antiquarks, which form a pion, can't go very far either because they will eventually annihilate. But there's a metastable state. They exist for a small amount of time, long enough for them to leak out of the baryon and bridge that gap from one baryon to the next. So 𝗟𝗶 said that pions were responsible for the strong nuclear force. And he's not entirely wrong. They're responsible for the residual strong nuclear force. That's the force, the strong nuclear force, that leaks out of baryons, and the reason why baryons bond together within the nucleus, which is what 𝗟𝗶 was trying to describe. 𝗟𝗶 didn't have a quark model. So he was trying to explain why protons and neutrons stick to each other in the nucleus. And actually, pions give you that explanation. They act as a conduit, a bridge from one baryon to the other, so that the strong nuclear force can get out of a baryon. What's not shown in this little animation is that you will also get quarks and antiquarks created in equal measure within the baryon constantly in flux. The mass of a proton cannot be pinned down, or a neutron or any other baryon. You can't pin it down because within that gluon field inside the baryon, you will always get quarks and antiquarks being created and annihilating each other, as well as these 3 quarks. So these 3 quarks are sometimes referred to as the valence quarks because they reveal to you what the baryon is. Within that baryon, there's still a soup of gluons and quarks being created and destroyed constantly, and in doing so, changing the colour of these quarks. So the strong nuclear force is mediated by gluons, but the residual strong nuclear force is mediated by pions. Now, the idea that gluons exchange gluons with other gluons can be quite a complicated idea. But what it means is that the further apart you try to get two quarks that are exchanging gluons, the more gluons you'll get between them. And these gluons will attract to try to form white, to try to have a color-neutral particle. So if you have a look at this picture here, we've got 3 gluons indicated with these springs and 3 quarks. And if I pull the blue quark out a bit, then now the gluons here exchange gluons with the gluons here. It's a bit difficult to see. I hope you can see the mouse cursor okay. But the gluon between the green and the blue down quark is exchanging a gluon with the gluon between the up and the blue down quark. And if I continue to pull that blue quark out, then I have more and more gluons being created within this field. The energy, the work that I do in moving that down quark is stored in that gluon field. And eventually, if I pull hard enough, then there'll be enough energy in that gluon field to create more mass. And we'll create equal quantities of quarks and antiquarks, in this case a down and an anti-down. We've created as much matter as antimatter. That's allowed. You can do that with the strong nuclear force. And the matter has come from the energy stored in the gluon field. So a question might be, well, how is it that you pull a quark out? You can't actually get a single quark by itself. You cannot isolate it. Because when you try to pull this quark out, the gluon field collapses into a quark and an antiquark. You can't get a solo quark by itself. This is what's done at places like CERN, at particle colliders. By colliding baryons together, you're trying to knock quarks out. You can't get the quarks to be knocked out, but by doing that work on those quarks, you increase the energy stored in the gluon field until it collapses and decays. You're doing more work on that quark, which means more energy stored in that gluon field, which will then collapse into a quark and an antiquark pair. So underground tunnels like this have these evacuated chambers that are very, very long and have protons accelerated around them so that those protons can collide. When the protons collide, we create new matter because of that strong interaction. Because we're trying to knock quarks out, which increases the number of gluons, therefore increasing the gluon field, and therefore that field will collapse when there's a sufficient energy stored into a quark and an antiquark. Now, we talked about decay of fundamental particles and how the weak nuclear force is the only force that can decay fundamental particles, that is, elementary particles. But what about composite particles? Well, we'll have a look at those in the next and final episode of this series.